waveforms for a voltage which is sinusoidal, and that we can represent, let's say, VDS equals VDD minus VDD cos theta, which is a very simple class B drain voltage waveform, and current waveforms, which is a half sinusoid. With that half sinusoid, if we expand up to third harmonics, we can represent that half sinusoid class B waveforms like this up to third harmonics. Point to be noted here is that for the drain current waveforms, we don't have any odd harmonics to be generated for a half sinusoid current waveforms. Actually, if we look at these two waveforms, we literally can have all the information for a class B T operation. Literally, it's gonna describe of its whole operation. So, I mean, in terms of operation, we would like to know what would be its terminations looks like in terms of design space. So when you say design space, that means what would be its fundamental termination, what would be its harmonic terminations. As you can see, since there is no higher voltage components being generated, so eventually second harmonic and third harmonic termination is going to be short circuit. And for the fundamental, which we are calling R opt, can be again computed with the real and reactive component from the voltage and real and reactive component from the current. So if we take the real and reactive components from the voltage and current and put into this equation, we actually can find out what would be the R opt for this class B operation. And we see that would be 2 VDD over Imax. And with that, we can also compute, let's say, for any given device, if its current, I'm just showing one example, if its current is, let's say, around 2 ampere maximum current and operating at 50 volt supply rail, its R opt is going to be computed as 50 ohm for class B operation. Well, with that, you literally can start designing for a class B PA, which would operate for about 78.5% efficiency, provided there is no voltage, no knee voltage is accounted. So, I mean, similarly, like how we computed the design space, we can also compute the output power, DC power consumption, and efficiency from these two basic drain voltage and drain current equation. So one very interesting thing for class BPA is that you see there is no harmonic voltage in class BPA. Since there is no harmonic voltage in class BPA, although there is harmonic currents being generated, there will not be no harmonic power will be generated. So now the point is, here is no harmonic power has been generated. Why efficiency is still 78.5%? Why it is not 100%? Because no power is being wasted for harmonics. What is really happening? Well, the point is, if you see literally for a class B waveforms, there are some overlapping between the voltage and current components, voltage and current waveforms. So since they are overlapping, definitely there is going to be some power dissipated across the device. So now then again, it's a point to refresh that power conservation in a RF PA is that all the power we are giving into the PA, like DC power and the input power, would be equal to output power at the fundamental, output power at the harmonics, as well as the power dissipation. So not only that you can lose efficiency of a given device by harmonic power generation, also if there are some overlapping between the voltage and current waveforms, you can also lose the efficiency. And that's why for high efficiency operation, we definitely need to watch out for two things. One, we would like to maintain the harmonic power generation as low as possible, as well as power dissipation to be as low as possible. So after that, in fact, all the harmonic tuned PAs are evolved keeping that in mind to reduce the overlapping between the waveforms, so that lowest power dissipation happens. And at the same time, all the harmonic tuned power amplifiers, very interesting to say, uses the harmonics so that no harmonics power actually gets generated. So that it uses the harmonics termination to shape the voltage, no power dissipation. Ideally, no power dissipation and no overlapping, or as minimum overlapping possible between the voltage and current waveforms. So here is one very simple example for ideal class F power amplifiers. You see, for ideal class F, we still have the half sinusoidal current waveforms, while it's proposing the voltage waveform to be square shaped. Now, if we check the Fourier components of this half sinusoidal current waveforms, it's the same as class B. Nothing changed in terms of the current waveforms of a class B. Still, it has all those same components. It only generates the even order harmonics. On the other hand, if we check the Fourier components of a square wave, it does the opposite, meaning it generates only the odd order harmonics. So if you actually try to see the harmonic power being generated by these two waveforms, that would be completely zero. So no harmonics power going to be generated. That's how we minimize the harmonic power loss. At the same time, if you see visually, there is no overlapping between the voltage and current components. So, with the ideal class F power amplifier waveforms, you will get efficiency of 100%. So, but then what happens? Why we don't get 100% efficiency in practice for a class F? The problem is that if you see, to realize these ideal waveforms, of course, you need to have infinite amount of harmonic terminations, which is not gonna be possible in reality. So what happens in reality? Possibly we can consider up to third harmonics of termination. So for that up to third harmonic termination, what we can consider, let's say, current waveforms and voltage waveforms. Current waveform still remains the same as class B, and we can shape the voltage waveforms by introducing a third harmonic voltage components. How do we do that? To introduce that third harmonic voltage waveforms, we terminate third harmonic load at the open circuit, and since to maintain second harmonic power generation to be zero, we maintain second harmonic termination to be at short circuited. So by that, we end up having still half sinusoidal current waveforms for class B, and we shape the voltage from sinusoidal to rectangular like. It's not a perfect rectangular waveform, but it's more like a rectangular, very close to that. We are considering up to third harmonic, so the price is there. But still, we try to maintain very close to rectangular waveform shape voltage there, and try to minimize the overlapping between the current and voltage waveforms as much as possible. And that way, we improve the efficiency of a class F power amplifier from class B up to 90% from 78.5%. Similar thing happens for inverse class F power amplifier. Here we do the opposite. We have now half sinusoidal. This is again for ideal inverse class F operation. We have half sinusoidal voltage waveform, and then we have rectangular current waveform. So we shape both voltage and current from starting from class B. Again, we don't have any overlapping. If we see the Fourier components for the voltage and current, we see no harmonic power gonna be generated. That way we maintain again 100% efficiency for ideal class F inverse. Again, the catch is that we cannot have infinite amount of harmonic terminations. That's how we cannot realize 100% efficiency ideal class F inverse. So the reality would be we try to opt in for up to third harmonics termination. That way, we still try to manage very close to half sinusoidal voltage waveform and close to like rectangular current waveforms. Well, the catch again, how what Joe was presenting at the very beginning, by introducing this second harmonic voltage component into the voltage waveforms, we are actually peaking the voltage. That way, it's almost 2.9 times the VDD. So definitely, the breakdown of the device has to be higher than VDD by 2.9 times. Otherwise, that's the catch. Class inverse class FPA cannot be also realized. So if we compare them closely by how they look like in terms of fundamental and harmonic terminations and in terms of efficiency, here is the quick summary. For class B, we end up having 78.5% efficiency almost. And point to be noted that all our harmonics has to be short-circuited. And for maximum efficiency class F, when I say maximum efficiency class F, that means it's up to third harmonics consideration. We reach up to 90% efficiency from like 78%. And similarly, for inverse class F, we get a little bit higher than maximum efficiency class F. So point to be noted here is that our fundamental impedance are significantly different from class B. More towards we are going to higher efficiency classes. You can see that fundamental impedance termination is also increasing in terms of magnitude. Well, it would be also interesting to say it's not only a theory actually. In fact, if you try to terminate the proposed terminations for fundamental and harmonics, you can end up having the similar waveforms what we are theoretically deriving. Let's say, for example, if you take one device and terminate similarly like ROP for class F and make your third harmonics around open circuit and second harmonics around short circuit, you see your drain current still remain similar to half sinusoidal, while drain voltage is shaped around rectangular waveforms. So by that, you end up around 80% efficiency. Well, you might ask that why it is 80%, why it is not 90% than theoretical. Well, a practical device is going to have its knee voltage. By knee voltage, you typically trade off 5 to 7%. And also another point there here is that third harmonics, it's not intrinsically perfect open. So it's still representing some loss there. So, I mean, you still end up having around 80% compared to 66 to 67% of a realistic class B efficiency performance. Similarly, for a inverse class FPA, if we terminate second harmonics around open and third harmonics around short, you see we can in fact shape the drain current towards rectangular, looks like one, and the drain voltage again, it's a half sinusoidal, and if you see, it's a 28 volt device operation, and BDD is about 3 times that supply rail. So what I'm trying to show here is that all the theoretical calculation still holds very well as long as we are presenting the right impedance and intrinsically to the device. And if we can see that efficiency is up to 85% compared to the theoretical 91% of efficiency. Again, it's not exactly 90% or 91% efficiency to the theoretical computation because of the knee voltage of the device. So far, what the PA classes we have been discussing, those are, you can see, single point of impedance termination. But the point is, it's very difficult to realize a perfect short or perfect open um, for a broadband operation. So eventually, we cannot. I mean, this single termination is good for single frequency of operation, because when frequency will change, of course, impedance termination is going to be changing from either open or short circuit. So what should you do? That's how continuous mode PA was introduced by Cripps and his group. Just a quick summary. Again, how the waveforms, I'm going to discuss from waveforms point of view, how the continuous mode PAs look like. If you see, for a continuous mode class BJPA, the current waveforms still looks like same as class B. It's exactly the same. But what has been shaping here is that the drain voltage, to find a mathematical solution, it takes some reactive components for the fundamental and reactive component for the second harmonic drain voltage. So that's how it shapes the voltage. So the question is, why it opting to shape the voltage? Why not the current? First of all, if you check the current of the class BJ waveform, there it already reached to the Imax. So Imax of the device. Time to time, we see a lot of papers sometimes attempted to write where actually waveforms are considered which is crossing more than Imax. That's actually going to be misleading to some extent. So we shouldn't actually come up with some waveforms where current is crossing Imax. So in class B, current already reaches to Imax of the device. So this is normalized 1. That is the Imax of the device. So if you start introducing reactive components there, it will start speaking left and right, which is going to cross the device Imax, which would, although mathematically you will find a solution, but it's not going to be a realistic solution, and the efficiency and all the solutions will be misleading from the practical ones. So since there was no room for current peaking left going beyond Imax, but for a GAN device, typically the device breakdown voltage is more than 3 VDD or even more. So there was a room to start peaking from the 2 VDD more than towards left and right. That way it can reach there. So the point is, there is a room to shape the voltage higher than 2 VDD, and that's why it was chosen to introduce reactive components into the voltage to have a broader design space. Again, since we got all the current components and the voltage components, you can calculate the design space, like fundamental impedance, second harmonic impedance, and third harmonic impedance is going to be short-circuited. And that way we can have voltage shaping, and current remains still the same. Since there is no change from the real components of the current and voltage, still all the class BJ termination has the similar efficiency like class B. Similar thing happens for continuous mode class F. Again, for class F, its current is same as class B, and voltage shaping again happens from its rectangular like voltage waveform. It introduces reactive components into the voltage, and that way it shapes the voltage from rectangular to left and right. Voltage peaking happens. Again, you see the voltage is increasing from 2 VDD to almost 3 and 3.5 times VDD. So again, the caution is that if the device doesn't have enough breakdown voltage headroom, continuous mode class F cannot be realized, or it can stress the device and can decrease the lifetime of the device. Similarly, for continuous mode inverse class F, it does keep the same voltage for the as it is like inverse class F, but it does current shaping. Again, why current shaping? If you see again, voltage already reached to 3 times VDD from inverse class F. If we do further voltage shaping there or further voltage peaking there, it's going to be so high voltage swing, it can actually go beyond the breakdown voltage of the device. But on the other hand, if we check the nominal voltage for an inverse class F, it has a room to reach up to still IMAX. It's typically, if for this plot, 1.2 was the maximum current of the device, while for the nominal inverse class F, it reached around 0.7 amperes. So it has room to peak current left and right to reach to the IMAX. So that's why for in continuous mode inverse class F, current shaping was chosen. Anyway, by this continuous mode, we now have a broader design space, which is good for broadband PA operation. So by that, we would like to start input-output waveform engineering. So with all these works, we try to consider input harmonics to be short-circuited. And one of the reasons was that initially we thought input harmonics actually sometimes can cause performance degradation in terms of efficiency and output power and also linearity. So, but the point is, for a broadband operation, we cannot again maintain the second harmonic source termination to be at fixed short circuit termination. Because for broadband operation, when frequency will change, again, the second harmonic source termination is gonna be again changing from its short circuit ideal termination. So on other sense, what we can say that non-short circuit termination for second harmonic source is going to be the reality. So that's why then we need to understand what really happens for non-short circuit second harmonic source termination. So first of all, I mean, why do we care for second harmonic source termination? What's typically the source of it? Well, the main source of input nonlinearity is its CGS nonlinearity. So when we excite the input of a device with a sinusoidal waveform, due to the CGS and VGS nonlinearity, and based on the termination we are presenting, its voltage can be shaped into different waveforms. Like one example here, if there is no input nonlinearity, it could be the black one. I mean, it could remain as it is, whatever the input is, sinusoidal. But based on the input nonlinearity, it can be shaped rectangular. It can be also shaped, also peaking in different magnitude of voltage. So more example here. So to quantify that, we literally can model the input nonlinearity. Let's say when it is linear, like one sinusoidal, we indeed can consider from V1 cos theta to this. When we are considering up to second harmonic source, we introduce a second harmonic voltage, input voltage component. And if we normalize it, we can represent that normalized voltage into this one. And from that point, we introduce two parameters. One is gamma and phi2. By gamma, we are meaning that V2 over V1, that means how much second harmonic voltage we are considering compared to the fundamental input voltage. And phi2 is actually the phase difference between the fundamental and the second harmonic component. So by that, now we can actually see if we have different level of input nonlinearity, how the waveforms can be shaped and to what extent. Let's say I'm plotting different waveform when phase is changing from 0 to 1.5 pi, and in each plot input nonlinearity factor, I'm changing from 0, 0.25 and 0.5. As you can see, the waveforms are shaping in different types. One quick observation, you can see that sometimes waveforms are getting contracted, meaning when your gate voltage is getting narrower, when it will be translated into the drain current, definitely your conduction angle is going to be changed. On the other hand, from the nominal black one, if you see here in this example, the waveforms are getting extended. So from normalized, if we take from 0 level, that's going to be transferred into the drain current. So from the black one to the red one, you see this is more like rectangular shape and extended shape. For that one, the device conduction angle is going to be changed or increased. Again, if we consider what might be the impact, definitely when by voltage shaping, since the conduction angle of the device is going to be increased, we can expect that efficiency performance is going to be decreased. Similarly, when the conduction angle is going to be contracted, we can expect its efficiency is going to be to some extent improved. So by that, we can actually can compute how the conduction angle is going to be changed by introducing the input nonlinearity. Here is one example. So we start from class B operation. So nominal conduction angle is 180 degree. Now if we change gamma and phi2, gamma from 0 to 0.5, for example, and phi2 0 to 360, we see that a different combination of gamma and phi, phi2 can change its conduction angle to different values starting from 180. Sometimes it's increasing up to even 220 degree from nominal 180 degree, while it can be also decreased to 150 degree. So same thing is going to be reflected into the efficiency performance. When you see that conduction angle is increasing, similarly, efficiency got decreased, and vice versa. When conduction angle in the region where it is decreased, efficiency has been increased. So as we expected, right? Now the point is, we understood what happens when input nonlinearity is there. Of course, it can, when input voltage gets shaped, it directly impacts the efficiency performance of the device. Now the point is, how can we ensure what kind of termination of second harmonic can do what? So we need to correlate the second harmonic impedance termination to this gamma and phi2. In fact, we can do, if we model the input nonlinearity as a polynomial, like the capacitor and the input conductance as a polynomial. And in fact, we can find a relationship between the second harmonic source termination as a function of gamma and phi2. That way, we in fact can see what will be the generated gamma and phi2 if we terminate second harmonic source around the edge of the Smith chart. So here we are terminating second harmonic on the edge of the Smith chart around the Smith chart, then we can see what's the gamma and phi 2 being generated. You see, most of the cases phi 2 remains around 180 degree, but in certain region it spikes out. So that point needs to be carefully monitored. And similarly, most of the cases gamma remains around 0.2, while at some point it can have a very high value up to 0.6 and 0.7. So, so again, this calculation was done for again 2 millimeter at frequency of 1 gigahertz, while fundamental was terminated at MXC. Now the point is, so literally this plot is telling what are the possible gamma and phi 2 combination. Now the design space, what we can see, if we plot that gamma and phi 2 onto the efficiency for different class of operation, we can see literally these are the possible efficiency region we can extract by exploiting the input second harmonic source for a class B. So although there are 88% possible region theoretically, but practically we cannot realize that because of the CGS non-linearity. What is possible from the device, it can only opt in for this zone for class B. Similarly, for this zone for class F. Well, still we can reach up to around 83% or 84% compared to 78.5% for traditional class B. Similarly, efficiency can be increased to 4 and 5% for class F theoretically, and same thing for inverse class F. So now, instead of sweeping the second harmonic source around the Smith chart, at the edge of the Smith chart, we can actually do a second harmonic source pool on a full Smith chart just to see what happens and have a nice demonstration how different class of operation actually behaves with input input source pool or second harmonic source pool. You see, for class B, there are regions where efficiency can be severely affected, which is guiding us. For a class B design, we need to avoid this region to have a nice efficiency performance. While compared to the short, we have a very small region where efficiency can be improved to 75% compared to 66% of its class B operation. And similar trend we also see for class F. It is quite changing around the Smith chart. That's how it is telling that both class B and class F are very sensitive to second harmonic source termination. So as a designer, you need to be very careful how you are terminating your second harmonic source. You see, you can end up having 87%, and if that is not terminated, you can end up having like less than 50% efficiency. So it's a drastic change. And as a designer and application developer, you might get in a huge trouble if you don't take care of the harmonic second harmonic source termination. On the other hand, if we check for inverse class F, you see it's for the huge area on the Smith chart. It's a very constant efficiency. It's literally telling inverse class F is more immune to the second harmonic source termination, but still there is a region where efficiency still tanks. So that's why still you need to be very careful to avoid that small region so that you don't end up trapped into that bad region for inverse class F. But good thing here is that most of the cases, most of the region is very good for inverse class F, and it shows excellent immunity to the variation of second harmonic source termination. So what we are literally seeing is that inverse class F is an excellent candidate for both input-output waveform engineered high efficiency PA design. But again, what happens for inverse class F is that it has intrinsically very high AMAM distortion. So one of the paper actually discuss what's the source of it. So I mean, the fundamental condition for this AMAM variation is mainly because is that at the very low power region, because the second harmonic source termination, second harmonic load is open for inverse class F. That means G2L is very high. The voltage swing because of that G2L, although at very low power I2 is very small, but the product of I2 G2L can be very high. And at low power, that's how it can swing back to the knee region and start compressing the device. So that's one disadvantage of inverse conventional inverse class F. Because of the high Z2L component, it generates high V2 component, which is the I2 Z2L, and increase the voltage swing significantly even at very low power and start compressing the device. And that's why you can see even at 15 dB back off, it has started compressing the AMAM, and it keeps going like that. So that's one limitation for inverse class F to realize in commercial application, because it's not only that we can get whatever efficiency you want, but at the end, if it is not linearizable efficiency, that efficiency not going to be any useful. So next, the target is, can we shape it so that we still can have good efficiency and at the same time good linearity, or at least can we correct this AMAM distortion? So in fact, if we consider the input non-linearity again, we can see that based on gamma and phi 2, our current components can be changing. So what happens if we check for different values of gamma, we can see that second harmonic current components for a drain current can be starting positive, and for after certain value it can go negative. You know, that is giving the clue that, well, if we come back to this equation, so the condition for AMAM inflection is that the addition of all this voltage V1, V2, and V3 component has to be more than VDD minus VK. Now, if we actually lower this value of I2Z2L by lowering the second harmonic current component, we actually prolonging the power drive up when it's going to reach to the knee region, because we are lowering the product of I2Z2L. And that how, in fact, at some point, we can even make it negative. So instead of having instead of reaching to the knee region at the very low power, it can actually even deliver more fundamental voltage component. That way it can in fact improve the power density of the device. So from that point, if we see, if there is no input non-linearity gamma equal to 0, it hits the knee region almost like 10 dB back off, while if we increase the gamma, we can drop the I2Z2L component, and it doesn't necessarily now need to reach that VDD minus VK, and it can only reach to the compression level when it reach to the preset power. So by that, we can we can see how that happens. For example, you see for class F inverse or conventional inverse class F, which is the black one, it's already reaching to the near region, while with the second harmonic source optimized, it can still maintain a flat AMM characteristics. And thanks to Damon for all these plots. He was the mind behind generating all these plots and helping us. So similarly, I'm showing here is the same point, while for inverse class, if it hits the near region at the very early power level, with the optimized second harmonic source, we still can maintain the flat AMM characteristics. So by that, we introduced another class of power amplifier operation, while we can keep the high efficiency as well as linearity for the power amplifier. You can check the paper I cited here, that was published in TMTT by Chen-Hao Chu. So for more details, please refer to that paper. But yes, what we can see that without minimum efficiency sacrifice, we can correct the AMM distortion of the inverse class F by exploiting the input non-linearity. So again, we can see the comparison between inverse class F and class F at. So we can compare at constant SCPR and at constant P out. Let's say if we consider we need to design the PA at constant minus 30 dB if we compare. So we can see that PAE for inverse class F reached to 35.4%, while that constant minus 30 SCPR can be actually almost 5% higher than inverse class F. The point is, since it starts compressing at very early power level, so that's why its SCPR degrades and linearizable efficiency is reduced. Similarly, for constant P out, we can see that for class IF inverse, it improves by almost 4 dB SCPR, while maintaining the PAE almost similar. And here is one quick measurement comparison. We can see that while class F inverse shows that gain compression from the very early power level, IF inverse can maintain that flat gain up to the P set, or at least up to P1 dB. And here is one interesting input design space we are showing, that is, it's not only one single point, we can maintain that high efficiency and flat gain. It's a complete and wide design space for input for inverse class F, where we can maintain both linearity and efficiency. So by that, I would like to conclude. Well, waveform engineering definitely is instrumental to extract the PA performance to its best, but it become also tricky because there are bad region in terms of harmonic terminations also good. And not only that, it also involves iterative terminations in terms of fundamental and harmonics, so that it's not that all the fundamental terminations are good for all the harmonics, so it has to be adjusted based on harmonic terminations. So that's how it become to some extent tricky, because sometimes we see, oh well, we terminated the second harmonic towards open, which is supposed to be inverse class F, but I don't get that high efficiency. What's the reason? But well, there can be 2. For example, the fundamental load has also need to be adjusted, and as you can see, second harmonic or input non-linearity has also need to be taken care carefully. Well, by that I would like to go to question and answer. Thank you.